Welcome back. Problem 8.43. So, a 10 kilonewton force and 1.4 kilonewton meter couple are applied at the top of 65 millimeter diameter brass post shown. Determine the principal stress and maximum shearing stress at point H and point B. So, you can see this is a brass post and a 10 kilonewton force is applied on this face and 144 kilonewton meter into meter couple is applied. So you have to find the principal stresses and maximum shear at point H and as well as at point K. So let's start with the solution. Now you can see that if you take the reaction over there, so definitely at this base, so you will know that at this base if you remove this support, so there will be a shear force that will be acting in opposite to this 10 kilonewton, and this will be equal to, again this will be also in 10 kilonewton, and due to this 10 into perpendicular distance is, this is 10 kilonewton and perpendicular distance is this, it will cause the this brass post to bend. So definitely there will be a bending moment, and that bending moment will be in this direction. Clear? I will write this. So shear force V at the end is equal to 10 kilonewton. Clear? The bending moment will be equal to, load is 10 kilonewton, so 10 into 10 raised to power 3 newton into perpendicular distance is 240 millimeters. So 240 into 10 raised to power minus 3 will convert it into meter, and the unit will be into newton into meter. And that will give you, moment will give you 2.4 into 10 raised to power 10 raised to power 3 newton into meter. And also there is a torque couple is given, so it will be equal to, in this here it will be opposite to that, and this torque will be equal to 1.4 into 10 raised to power 3 newton into meter. Now we have been asked to find the principal stresses at point H and point K. So at the section we will write at the section containing point H, containing point H and K, there are certain properties that we should know. So this radius or this diameter is this diameter is equal to 65 millimeter. So diameter is equal to 65 millimeter, and from here you will get radius which is equal to d over 2, and that is 65 over 2 and 32.5 millimeter, or you can say C in term of meter will be equal to 0.0325 meter. So this is the radius of brass post. We will also calculate polar moment of inertia J, and that J is equal to pi by 2 C power 4 for circular shaft. So pi by 2 C is 0.0325 power 4. So again from here you will get 1.7524 into 10 raised to power minus 6 meter power 4. Now we will also call the moment of inertia, and we know that moment of inertia is equal to half of J. As the shaft is circular, clear, so if this is its x-axis and it is, let's say this is y-axis. So we know that polar moment of inertia J is equal to, let this is x and this is y. So J is equal to Ixx plus Iyy. Since this shafts, this is symmetrical, so Ixx is equal to Iyy. So from here you will get J is equal to 2 times of either Ixx or Iyy, and let this is equal to I, and this I is equal to J over 2. So from here you can see I have already written that I is equal to J by 2. So you can put the value 1 over 2 multiply by 1.7524 into 10 raised to the power minus 6. Now you can calculate it, it will be 0.8762 into 10 raised to the power minus 6 meter 4. Okay, also for semicircle, that is given at the end of books. For semicircle, this Q, which is the first moment of inertia, is equal to 2 over 3 C cube. That is for semicircle. So you can put the value 2 over 3 into C is 0.0325 whole cube. So when you calculate it, you will get Q is equal to 22.88 into 10 raised to the power minus 6 cubic meter. Now we have this value, we will move toward our first part, that is about for stresses at point H. Okay, so for that we will draw the free body diagram of that shaft. So this was your shaft, this is your H point. Clear? I will show you, this is your H point. So if you take this is its neutral axis. So you can see, or from here you can see the H will lie on neutral axis. So I will represent it. Let this is its, this is the neutral axis, and this is not the H point. This is the H point at the mid. Clear? So also at this point, at this phase, we have, if we define the axis, so let this is your y-axis. Clear? This is your x-axis, and let this is your z-axis, y, x and z. Okay, so at this point C, we have 10 kilonewton force. So that is here 10 kilonewton force, 10 kilonewton. Also there is a moment twisting couple, that is 1.4 kilonewton into meter, and there is a due to this load there will be a bending moment, this, and this bending moment is 2.4 into 10 raised to the power 3. So 2.4 into 10 raised to the power 3 Newton into meter. Let me check. Okay, Newton into meter. Now stress at point H, this is your point H. Clear? So you can see, if I draw the top view of this, so this will be your circle, this is your neutral axis, this will be your point H. Clear? So as H lies on neutral axis, and we know that stress is equal to M into C divided by I. So C is equal to C is distance from neutral axis to the topmost layer. So this H lies on neutral axis, so it means that bending stress or normal stress will be, bending stress will be 0. Now we have a shear force on this face, so due to shearing stress will be there. So due to shear force, there will be a shear stress, and that shear stress is equal to V into Q divided by I into T. V we know that is 10 into 10 raised to the power 3. Q we have calculated this 22.88 into 10 raised to the power minus 6 cubic meter divided by I is the moment of inertia. I is this one, 0.8762 into 10 raised to the power minus 6, and total thickness of this shaft is 65 millimeter, which is 0.065 meter. So when you calculate it, you will get the shearing stress due to shear force, and that comes out to be 4.018 megapascal. Okay. Now you know that there is a torque or couple of 1.4 kilonewton into meter is also available. So due to torque, we have also a shearing stress that is equal to T into C divided by J. So T is 1.4 into 10 raised to the power 3. C is radius, which is 0.0325 divided by J is the polar moment of inertia, which was 1.7524 into 10 raised to the power minus 6. So from here you will get the shearing stress equal to 25.963 megapascal. Now total shearing stress at point H, total shearing stress at H will be equal to sum of this 1, let this is 1 and this is 2, is equal to 4.018 plus 25.963 megapascal, and that will be equal to total is equal to 30 megapascal. So what we have concluded that at point H, if we draw a element, so at point H there is no sigma is equal to 0 and total stress is this one. So it means that we have 30 megapascal only shearing stress. So this is your shearing stress. TH is equal to 30 megapascal. Now we'll move toward finding the principal stresses. So we know that for that we know that sigma maximum principal stress sigma 1 comma 2 is equal to sigma average plus minus R. So what is sigma average? Sigma average is equal to, there is no stress either in x or y direction, so sigma average is equal to 0, and R is equal to sigma average sigma x minus sigma y divided by 2 whole square plus tau of xy or tau square. Here we have total tau, so this term is 0 because there is no stress, so R will be equal to under root t tau square. So this R will be equal to after square will cut with this under root, so we have tau, and we know that this tau total is 30 megapascal. Now we know that sigma 1, which is maximum stress, principal stress, is equal to sigma average plus R. So sigma average is 0 plus 30. So sigma 1 max is equal to 30 megapascal. And sigma 2 is equal to, sigma 2 is minimum, and that will be equal to sigma average minus R. So 0 minus 30 is equal to minus 30 megapascal. So these are the principal stresses, sigma 1 and sigma 2, and this tau is the shear stress at point H. Now we'll move toward our second part, stresses at point K. So in B part, stress at point K. So you can see that from here, let this is your point H. So this will be your point K. This we will use in other color. This is your point K. And this is your neutral axis. So if I draw it over here, the same figure, or we can also copy it. So let copy that if it's feasible. So let me choose this, copy it, and we'll paste it downward. Okay. So now you can see that this is point K, and if I draw the top view, so this is the top view, this is its neutral axis, this was your point H, now this is your point K. Clear? So at point H, at point K, you see that due to shear force, the shearing stress will be equal to 0. Why? Because Q will be equal to 0 as it is at the outside periphery. Clear? So Q will be equal to 0. Now due to the disk torque 1.4, so due to torque we will have a shearing stress, and that shearing stress is equal to T into C divided by J. So you can put the values. Torque is equal to 1.4 into 10 to the power 3 kilonewton into meter, while C is 0.0. Let me check it. C is 0.0325 divided by J, and that J is 1.7524 into 10 to the power minus 6. So when you calculate it, you will get the shearing stress will be 25.96 megapascal. Okay. Also, you can see due to this bending moment of 2.4 into 10 to the power, so due to bending there will be bending stress. So this bending stress is equal to minus M into C divided by I. This is a clockwise. So minus MC divided by I, and the moment is minus 2.4 into 10 to the power 3, while C is 0.0325 divided by I is 0.8764 into 10 to the power minus 6. So from here you will get bending stress is minus 89.016 megapascal. Now if you represent it on state of two-dimensional state of stress on an element, so you can see that stress is negative, so it shows that this is compressive. Clear? And this will be your shearing stress, tau K. This is your TK, This is your sigma k. You can see this is Tk, this is tau k. So this is state of stress element. Also we know that we are going to find the principal stress is sigma 1 comma 2 at point k is equal to sigma average plus minus r. Now sigma average here is equal to minus sigma k over 2 because there is only one compressive stress. So when you calculate it will be 44.508 megapascal. Also R will be equal to this sigma minus 0. In x direction there is no stress, minus will be plus minus 89.016 divided by 2 whole square plus tau of xy. Tau of xy or tau k 25.96 square. So when you calculate it, you will get R is equal to 51.527 megapascal. And this R is generally represent in Mohr circle the radius. So definitely your maximum shearing stress will be equal to this R, and that is 51.5 megapascal. So if you want to draw it on Mohr circle, you can also draw it. I will draw it roughly. You will see. Let this is your initial axis because this is compressive. So I will delete this line. So here you will stress, and on y-axis you will have shear. So you can see that sigma k is minus 89 megapascal and shear stress is 25.96 megapascal. So our first point is 0 because there is no stress in x direction. So 0 comma tk. So 0 comma tk will lies, let's say, here. You have to draw it as per scale. I am not drawing it as per scale, but just I am giving you idea. So your first is 0 comma tau of k. This is 1 2 3 3.5 1 2 3 3.5 and sigma minus 89. So let's say this is your point, comes out to be, let this is sigma k is minus 89. Let assume that. So you have to join these 2 points and you will get this center. Keeping this point C as center, you have to draw the, let's say this, you have to draw the circle. I am going to draw it roughly. This is not a complete circle. You have to draw the circle just like that. Okay, so you will get the circle like that, but this circle should pass through this point. Again, this is not a complete circle. I am trying to draw it. Okay. So you can see you will have the principal stress, which is this one, sigma 1. Your sigma 1 will be this one. This will be your sigma 1 maximum. And this will be your sigma 2. We haven't calculated sigma 1. So sigma 1 is equal to sigma average plus R. So sigma average is minus 44.50 and sigma plus R is 51.527. So sigma 1 will be equal to 7.0 0.02 megapascal. So if you draw it as per scale, you will see that this point will be 7.02 megapascal. Now sigma 2 is equal to sigma average minus R. So minus 44.50 minus 51.527, it will give you minus 96 megapascal. And again, you will see that this point will be sigma 2 will be equal to minus 6 megapascal. Also from point C to outermost, this is the radius, you can see, and this radius is equal to, this correspond to maximum shearing stress, and that maximum shearing stress is equal to R is equal to 51.5 megapascal. So this was the principal stresses at point K, and this is the maximum shearing stress. I hope you have enjoyed this video, and again, if you have any question, you can ask me in comment section. Kindly subscribe my channel for and keep watching the videos. Thank you.